So here we go. So we continue with natural gas, but just to recall a little bit, now I did made the pointer, but we talked about various uses of natural gas. In the worst case, it's a negative value, where we burn it, we don't know what to do with it, when it's associated gas that comes up from a reservoir that also has oil. And that's what's called flaring. And unfortunately, flaring is still done some places, but most places it's illegal to do flaring. And one can pump it back into the well, and one can pipe it in the pipeline, store it in compressed form in a tank. One can transform it to a liquid in various ways. We talked about some processes for that. Gas to solid, where we have natural gas hydrates. Gas to liquids, with synthetic fuels, then to make it into electricity, or we can make it into hydrogen, and different types of chemicals like plastics or fertilizers, and even make food in terms of protein from natural gas. So that has been mentioned as it could be a resource for the future, where one would actually make components for food to eat for animals or people from natural gas. So clearly it is a very valuable resource. But natural gas is constituted from many components. And the lightest one is methane, CH4, right? And that one is what we call a low carbon fuel. It has only one carbon for 4 hydrogen atoms. So that is really a very good energy source. And in many countries, or at least Norway, people don't understand that this is actually quite an environmentally friendly fuel. Then, of course, there are gas components that are heavier, like methane, C2H6. And if you compare the density, methane as compared with ethane, you see that it's more heavy. And then you can go to propane, and you have 2 forms of butane. Just the molecular structure is a little bit different between those two. But they are the same proportion in terms of carbon and hydrogen. And even beyond that, there are even more heavy components, because one can build these molecules by adding on more and more in these things that look like a chain, as you can see there. And one can, with modern chemistry, also take apart, when you have more complex molecules, you can take those apart and break it down into smaller molecules. But of course there is an energy term that enters into a process like that. So, and of course the very heavy gases like butane and propane are much easier to transport than methane. So that is the drawback with methane, as we talked about. We talked about by liquefying it, cooling down to minus 163, we can transport it. But remember, it's still a rather light cargo. So natural gas, where also methane becomes liquid, and minus 163, weighs maybe somewhere between 430 and 470 kilograms per cubic meter. It's light cargo. So volume is important. Weight is not the problem. And again, I don't understand why. I was a little bit confused when I showed you this the last time, because some of the things disappeared from the slide. Again, it did. But along this axis, it is really volume, right? So in the vertical axis, it's volume. And in the horizontal, it is distance to the market. So the solution you want to go for depends on how much do you want to transport and how far is it. And obviously, pipelines have the advantage that they have a big capacity, but it's virtually impossible to make it too long, so to speak. So that's the limitation with a pipeline, if you have to send it very far. And if you have very little volume and you have to send it very far, also that is uneconomic. Right? If you have a small amount of gas that you want to send very, very far, it's hard to make that economical. If you turn it into gas to liquids, also small amounts could be feasible. And if you have large amounts and large distances, and particularly large distances, that's where LNG really is the good solution. And then in between here, there is CNG, which is compressed natural gas. So instead of cooling it, we pressurize it. And now we'll look into what that means. Because there's been a very, very large effort over the last, in particular the last 10, 15 years, to develop competitive transport solutions for compressed natural gas. And from an innovation point of view, this is quite interesting. You know, how people have been thinking and what kind of solutions they have come up with. So, not only in terms of investment cost and, let's say, operational cost, CNG, compressed natural gas, has one advantage over LNG, and that is that you use less energy for the conversion. You know, the conversion from a natural atmospheric pressure to a high pressure, and then back again to, let's say, the pressure you want to have for the consumers at the other end. So less energy for CNG than for LNG. And of course, with pipelines, the amount of energy depends entirely on how far you want to pump it, because you have a friction which is proportional to the length of the pipeline.
In case of GTL, is the porting cooling, what would that mean?
That's the technology of, you know, for instance, one way of doing it is to mix it with water, and thereby also you have to remove the water, and the process for doing that can be still improved. I'm not a specialist in that field, but that is what is being indicated, that they are looking at various ways of improving that process. So, but of course, you have different ways of doing it. Also, you can transform the gas to fuel, right? We talked about that process too. Then, of course, you will not make it back into gas again, because that is good fuel like diesel you can make from natural gas. So, but the thing with CNG is that you have a rather, as we will see, you have a rather heavy design and quite substantial investment in the containment system. A LNG containment system is expensive, but a CNG containment system is even more expensive, much more expensive. And there's the safety aspect also, which is reasons for concern. So what is shown on this picture is where you have the main markets and where we have gas reserves within, let's say, the reach of a CNG ship. So you can see South Africa, in Asia, with gas in Indonesia, etc. Malaysia, some in Australia, and of course gas fields in Western Norway could reach markets in Europe. And you have gas fields along Sahara, which could reach markets in Europe, and you have from the Gulf, which could reach markets at least in India. But we know also they are planning on a pipeline from the Gulf to India. So that may sort of preempt the thinking regarding using CNG ships.
Professor, I have a question.
Yes.
You said the original paper doesn't use air. Is there any special reason why?
We don't use gas at all. We don't use gas for heating. We don't use. The only way we use gas is for some processing of and chemical processes, but not for as a pure energy source. But that is changing, and the change is that the coastal fleet is expected to be running on more and more on LNG. That means special engines on the ships that can burn natural gas rather than bunker oil or diesel, or maybe a combination of diesel and natural gas. And on Friday, I had a meeting with the president of DNV, Maersk Veritas in Norway. So we talked about future technology, and one of the things he was a strong believer of is that in the future, LNG will be almost the only possible fuel for ships. And that is because the international regulations are now becoming so strict that we cannot satisfy the emission limits by traditional fuels, certainly not by bunker oil, and even with diesel, it will be hard to do that. So in the future, there will be a big need for LNG for fueling ships. Think about that. So that is a major thing that's going to happen. So, and of course, it's easier to handle LNG than CNG. In principle, you could have pressure tanks on the ships and have CNG, but they are much more heavy. So that is worrisome. So, but we'll see certainly LNG tanks on regular ships for storing the fuel. So, but since there's been so much attention now over the last few years regarding compressed natural gas, we'll look a little bit into that. So, and one advantage is that if you have a remote oil and gas field, or particularly a gas field, you don't have a pipeline connection, what can you do? Well, of course, you can have a LNG FPSO, which could liquefy the gas and then, export it as liquid natural gas. But then you need big volumes to do that, because the investment in a liquefying plant is a major investment. So certainly you would not do that if you had a small production of natural gas. Right? But what you need for compressing gas is very simple technology. You need compressors, right? So those are industrial standard compressors that you can make use of to compress the natural gas up to 200 bars, 250 bars. It's a high pressure. But still, compressors can do that. And that is rather simple technology as compared with a large liquefying plant. So you clearly can see that you can handle smaller volumes with CNG, as we saw on that graph, where we saw that the CNG came into the picture for smaller amounts of produced gas than is the case for LNG. You see? Understand the situation?
My question is the compressor, because compressors works constantly and the operation cost is it requires lots of electricity.
Of course, you run those compressors on natural gas, right? You have the gas there. So, but as you saw in that graph, the amount of energy you need is maybe 3 to 5% that you have to do this compressing. But then again, on the other hand, it's very simple, because you have the energy stored in, you have the gas stored with a high pressure, and when you come to shore, you can connect to the pipelines for gas more directly. You don't have to liquefy it. You don't have to use energy like with LNG. You have to take energy from the ocean in order to heat it up to become a gas again. But with the CNG, what you need is a choke, so you don't burst the pipes. But otherwise, it's very, very simple technology, right? So that's the advantage. And so there's no insulation, or you can, of course, choose a strategy where you do a combination of compression and cooling. That is good. But the simplest technology, where you avoid to have a cooling system, is just to use compressors. So if you compare LNG and CNG, you see that the investment for either liquefaction or compression is much higher here than for CNG. What you have to spend on transforming it into the transportable form. Okay? But then, the ship and cargo containment, well, LNG ships are expensive, but CNG ships are much more expensive. So that's where you see that this middle part becomes very, very large. And then, on the receiving end, where you have to have regasification in terms of LNG, it's very simple, with some chokes and some other controls with CNG. So there are some comparisons, and if you like to, you can look at this again, comparing the pipeline with LNG and CNG. So there are some flexible costs and permanent costs. I'm not sure how much sense this really makes, but anyway, there are obviously some situations where pipelines are the best solution. Some places where LNG is best, and some where CNG is best. But again, the problem with CNG, if you have, for instance, at ambient temperature, let's say 15 degrees, you see you have to go up to 200, 250 bars before you get a very large capacity in terms of ton for a given size of containment. In this case, it's compared with 140,000 cubic meters of tank volume. Understand? If the tank volume is given and you compress it to 200 bars, you'll get only maybe 1/3 as much gas on board as you would get with LNG. And even LNG doesn't have a high weight density, right? So that it's a gas. You know, methane remains being a gas. So at ambient temperature, we just have to press it as much as we can. And that is quite expensive. And also, there will be temperature variations when you compress the gas because of the thermodynamics. You know, the temperature will go up, and when you take the gas out again, it will start cooling. And if you do it very, very fast, you can get areas which get very cold when you let out the gas. So that one has to think about also. So there are historically some work that has been done on CNG ships, and the first one goes back, as you see here, to 1960. And we can also see one design that was done in Norway in 1976, 100 bars, Saga Petroleum, which then became a part of Norsk Hydro, which then was integrated into Statoil in Norway. But that company developed a ship, 18,000 cubic meters in 280 bottles. And that's a problem when you have pressurized gas, and the same applies to CO2. Depending on what condition you do it in, you are ending up, at least if you are doing this at ambient temperature, with very, very many pressure vessels. And the reason is when you're up in 200, 250 bar, you'll see that, you know, the wall thickness, of course, is proportional to the radius, and you'll very soon end up with 3, 4, 5 centimeters of steel in the pipeline. And you use pipeline steel, by the way, because that is a seamless steel tube. So you avoid having to do welding if you can use pipeline steel. So that's typically what is done. And so, as I said, this is an area where there has been a lot of innovation, but one can say the optimal solution has not necessarily been found yet. And there are some that have a combination of pressurizing and cooling. And again, you have to look at the phase diagram for methane when you're planning your system. If you want to get it into a liquid, you can do a combination of pressurizing and cooling. You can have very thin tubes, and we'll look at this one, which is quite interesting. There are pipes. That's why it says pipes, is that it's pipeline steel, 250 bars, 200 CEATEC. These two are two Norwegian companies. TransCanada, Transocean Composites, and CEATEC. This company also has been working on a composite. So we'll get more into this, and I have actually myself been involved in quite a few of these. I came up with the first idea that actually was the basis for establishing this company, CEATEC. Also looked at their composite solutions, and I've also been looking at this coiled steel solution. So maybe I know something about it. But this is one example where you see these pipeline steels stored on a barge. And the details you find here. But this company, NRC, also has this kind of solution withstanding flasks or tubes, as well as a horizontally lying ones. This is this Knudsen have called CNG for PNG. I don't know why, but pressurized natural gas is the same as CNG. And you can see these batteries of containers consisting of maybe not so easy for you to see, but these are standing cylinders, pipeline steel, which are pressurized. And of course, it's not just pipeline steel, but you typically have a flask like this, and then you have to weld on a capping, right? So you have to weld this on. But this is seamless. There's no weld in the tubular steel. So that's where you have the highest stresses. If you look at the hoop stresses or ring stresses, as compared with the vertical stresses, what is the ratio? You should know this. The hoop stress, the ring stress, is exactly twice as much as the longitudinal. Yeah? So that's why it's important you really have to be concerned about if you have a weld in this direction, the highest stress is transverse, normal to the welding direction. So the weld is highly stressed, and of course the allowable stress in a weld would typically be less than in the base material. So if you can avoid it, that's good. And this is the interesting thing. As you see here, maybe I should point here. They use rather small diameter pipes like this, 168 millimeters, high strength steel, and they are coiled on a spool like this. And of course, the advantage is that you can have a very long, continuously produced steel tube that you wind around this thing. The disadvantage is that, of course, you get much more friction in the tube inside. If you think of 17 kilometers of pipe on one spool, and so there's you start taking out the gas from one end, right? The last gas has to run through 17 kilometers before it gets out, right? So there's a lot of friction. You know, probably it takes longer time to get the gas out again than it does with a large diameter storage. Right? But I was called to a meeting in Canada, in Calgary, in connection with this thing, and I pointed to them one problem they had not thought about, and that was rather simple in nature, because you know when you pressurize, the pipe expands, right? And you have all these cross sections of pipe that are stacked next to each other. They all expand, right? And since you have such a high pressure inside, you know, the expansion is considerable. Then of course you could have some confining forces, but these spools are flexible, so that is not the problem. But the problem that I showed to them was that because the stress in the hoop direction is twice the stress in the longitudinal direction, then the expansion in the transverse direction will be twice as large as the expansion in the longitudinal direction. So what will happen? And they had only done on, you know, small pieces of tubes. But the thing is that when this expands, the pipe will get too short. You know, if you took a garden hose and rolled it on a spool and you put water pressure on it, you'll see that it will start going backwards because it's, you know, the expansion in the transverse direction is much more than in the length direction, so it will start going back. And they hadn't thought about this problem. So, but I read last year that there was a contract between this company, Williams Cosell, and some company in Korea, where they have decided to start making this. So that would be interesting to see what their practical experience is. So maybe you could look it up on the net, see what the situation is. This is one that I was very much involved in, and I actually came up with most of the ideas for this one. And this is using steel pipeline attached to one side, and special ways of supporting this and how it's made, etc. But the problem is that the ship becomes extremely heavy. You know, there's there's more steel weight on that ship than the weight of the gas. And it's, you know, it's so much, these steel pipes are so thick that they barely float. Can you think? The weight per length, you know, because it's, I think it was 48-inch pipelines. And that's about the maximum diameter you can have. That's 1.2 meters. And is that 48? No, it's more. But the thing is that, you know, the thickness is also, I don't remember exactly, but in the order of 40 millimeters or something. Very, very heavy. So there were two ship owners involved, and they decided they wanted to go for a composite solution instead. This is the same company that then went into looking at carbon reinforced plastics, carbon fiber reinforced plastic. Very high-tech technology. We're using a company in the United States to develop this technology. But in order to make very large tanks, and you see here 3 meters in diameter, it's very difficult technology. And it's very expensive. And I'm not sure about the situation for this company right now. They have been working on this one for 3-4 years. They've done burst tests. A burst test you do not by pressurizing gas or air, but you use water. Because pressurized gas is terribly dangerous. You know, it's like a bomb. So it's much safer to use a more or less incompressible fluid like water. So that's what we do in the burst tank. So those tests have been done, but what the final answer is now regarding the cost and the economy of it, I'm not sure. And I added here a website, and I went in there today and looked at it, and it wasn't much news, so it doesn't look like they have a commercial project yet. It's tough to bring forward a new technology. One interesting detail is what you see here. So, indicating a subsea field where you have a pipe, flexible pipe for gas that can go directly into the ship by way of a turret. You know what the turret is? An attachment where the ship can move according to the weather situation around this attachment point. And you see that turret, lower part of it, which is more or less pulled into the ship, it has its own anchoring system. That's what you see there. So the ship is anchored via this attachment. So there's a company called APL that's probably the most advanced in the world when it comes to this kind of technology. So here's just a warning when it comes to pressure vessels. So there's no scaling benefit for pressure vessels. The material consumption is virtually independent of size. You know, that means the amount of material you use is directly proportional to the amount of storage that you want. So there's no real scaling benefit like having a big LNG tank. There's a scaling benefit because the surface area is only proportional to the length square, whereas the volume is proportional to the length cube. But in this case, with a pressure vessel, there is no such advantage. Very large safety factors must be applied. 3 to 4. Consequences of leaks must be considered and designed for. That is accident, doing hazard identification. Very important. Consequences. For instance, when you have a crack and compressed gas leaks out of it, you'll get a cooling effect next to the crack, which can make steel brittle. And then, of course, if you have a spray of very cold gas that hits another part of the structure, let's say the neighboring tank, there's a problem. Material degradation and corrosion. Yeah. And then you have some references here.